Okay, let's start. First of all, let's talk about our motivation. In real tasks, you often need large data sets to achieve good metrics, but there are some problems with them. First, it is impossible to collect large amounts of high quality data because if you will check every image, for example, by yourself, it will take too much time, and you can hardly obtain a very large data set. So you have to take photos automatically from internet, for example, or somewhere else, and some of them will have bad quality. Sometimes most of them. And there are different techniques how to solve this problem, but it is a problem. Another problem is that the larger data set is too expensive to annotate. So you can't, for small data sets, you can label it by yourself, or for bigger data sets, you can give it to outsource. But for very large data sets, it is too expensive to pay people for annotating so much data. So usual solution is to use self-supervised learning when you don't have labels, but your model learns data without labels. How is it possible? Well, in fact, during last lecture, you talked about unsupervised methods. Can someone remember some methods from last lecture?
K-means.
K-means, yeah, why? Good. Okay, for example, K-means. It is called unsupervised method because you don't have any labels. But to clarify, I will give another example for self-supervised learning. For example, let's assume we have a very, very big data set without labels, with pictures, for example, yeah? We want to train a model to understand the data, yeah? And for example, to classify the images, cats and dogs, let's say. But we don't have labels. If we have million of images, we can label, I don't know, 5,000 of them to classify, yeah? But other images are not labeled. What should we do with them? One of the approaches, first to pre-train the model to better understand the task, the data, and then fine-tune and then train it on annotated images. Let's see. So we have a very big data set, 1 million, for example, yeah, unlabeled, so only images. And a small data set, 5K, from pairs image label. Yeah. Okay. Let's do a trick. First take a model, and for every image, make a random rotation on 90 degree, 180 degree, 0 degree, or 270 degree. So divisible by 90. Do you understand what I mean? To rotate angle that is divisible by 90 degrees. And say the model to predict the rotation. Yeah. So from unlabeled data, we will obtain labeled data because the label is the angle that we rotate, and train such model on this task. This wouldn't help us to predict label, but it will make the model understand the rotation of the image, and this will help. And how the model can understand it, how the person can understand it. For example, if I see a cat and it's I don't know, its feet are at the up of the at the higher than, for example, its head. Yeah, I can say that the image is rotated by 180 degrees. So something like this. I don't know. This is the face, ears, yeah, body, and feet. So this helps us to say that that the image is rotated. How on which angle? The same as the model, it starts to learn how to predict the angle, and it starts to extract useful features from this image. For example, where are feet, where are face, where is face, where are ears, and so on. So this method helps the model to extract useful features. And usually this model constructs like feature extractor or backbone, yeah, that takes the image and returns feature map. We discussed feature map, for example, on lecture about object detection. Yeah, we said that there are models that encode input into the feature map. It is smaller, but contains as much information, global and local information. In our case, I think it's more about global information because after we have the feature map, we usually use something like linear layer that predicts, in our case, the angle for classes. Yeah. So we have a classification task that predicts the angle and on unlabeled data. Any question? Any questions? Okay. Send some images if you understand what is going on. Please.
But like if our initial images are already rotated, would it predict correctly?
Sorry, we rotate each image by ourselves randomly. So initially they're not rotated. If they're initially rotated, you ask. Usually, if you get images, they're not rotated because if you photo something, yeah, you don't photo it. You're photoing in right orientation without rotation. So usually you stand on ground, yeah, and photo image in usual method. So if they're initially rotated, the method I think hardly will work. But in fact, I think in every case, images are not rotated, so it's okay. Okay, so we pre-trained the model. Yeah, we have backbone, we have and linear layer, and the backbone now we want the backbone to extract useful features. And our idea is after pre-training, it will extract useful features. And after we take another linear layer and the same backbone. In fact, new model will have the same backbone with the same weights. That is important. So we use the same weights. Yeah. And now and again, it extracts features and we use linear layer. But now with a new number of classes. For example, we have cat or dog. only two classes. Yeah. And the idea is that before we will take first example from 5,000 labeled data, the backbone will already extract useful features. And in fact, the training will focus on the, not on, most focus will go on linear layer. Okay? It's a little bit incorrectly, but we will talk about this, about focus. So our idea is that after pre-training, the train on label data will go faster and we will achieve better results because our model, compared to first approach where we only used 5,000 images. Now our model saw also 1 million images, and it will be more robust. It will get more accuracy and so on. Okay. So this method calls pre-training. So we first pre-train model, and after second step is called fine-tune or linear probing. We will talk later about differences. Okay, any questions? Okay. Yeah, in fact, instead of predicting angle, we can use many other tasks. For example, painting. We take image, make it grayscale, and ask to the model to paint it, or paint, for example, some areas. We make gray some area like this, yeah, and ask model to paint it. Or we can mask some areas, yeah, mask some areas, and ask model to predict what was under the mask. And so on. There are different masking techniques. If you want, I can give you extra materials about them, if you ask. Okay, so rotation is only an example. Let's go on. Just a second, I will clear all drawings. Let's go on. So as I said, this is pre-training. This is our backbone, output feature map, and network head. It's not always linear layer. It can be a multi-layer perceptron or something like this, but usually linear layer. Yeah, and we get outputs and use them for loss, pre-training loss. Yeah, pre-training loss and fine-tuning loss are different because, for example, pre-training loss in our case is predicting degree classification, and fine-tuning loss is predicting real class, cat or dog. So different losses. For example, training can be regression task and fine-tuning classification. So big difference. Then goes fine-tuning. During fine-tuning, we take model from pre-training, drop pre-training head, and use another head for our downstream task. Downstream task is like classification cat to dog. And use the same network with initialize it with the same weights. And then we train the whole network on our downstream task and use downstream task loss. I said everything before. And now linear probing. What is the difference? The idea is the same. We drop network head and use another, but now we freeze backbone weights. So during downstream linear probing, we don't change weights of backbone. So our feature map is frozen. At the end, our backbone will give the same encodings for each image as after pre-training phase. Okay, do you understand the difference of linear probing and fine-tuning? In fine-tuning, we don't freeze backbone. It can change during fine-tuning. And in linear probing, it is frozen. Any questions? Great. Okay. Why we have two methods? What method is better and when? First, let's talk about difference of in distribution and out of distribution data. Well, it's a little bit it's not very strict definition, but you can say that in distribution data is data from the same distribution as the pre-training, and out of distribution is another domain. Is similar like the pre-training data, but from another domain. For example, if your data during pre-training 1 million images were about bananas, yeah, you can see them on the left. Yeah, sorry, I had to say it. Said it during linear probing. We don't change backbone, but we change head. So in fact, during linear probing, you take encodings of each image, and they go as input to linear head, and this head classifies, for example, cat or dog. And we change only weights of linear head, and the network backbone is frozen. We don't change weights. Okay, great. Let's return to our in distribution and out of distribution. So if in 1 million data were about bananas, and during fine-tuning, for example, on 5,000 samples, you have the same bananas, I don't know, on trees, in basket, or something else, it's in distribution. But if you have left images of bananas in pre-training, and during fine-tuning in 5,000 samples, you have drawings of bananas, this is out of distribution. Yeah, there's the same bananas, but the same classes, but another domain. Sketches, for example, or pictures. Got it? So, there is a statement that fine-tuning is better in distribution tasks, and linear probing better in out of distribution tasks. So if you have the same data, you can change. It's better to change weights of backbone, and if you have another domain, for example, pictures of bananas, it's better to change backbone weights. So it's better to freeze that. Okay. Next, we'll talk about why is so and what to do. Okay. Yeah, in one of the papers, as far as I remember, 2022, the paper proposes the explanation of this fact. Let's take a two example where our backbone is a linear layer, B backbone. X is a linear head, and V is our in-domain data. So we have a loss. First, we take V, our input, applies to it our backbone, B, and then apply to it X. Because these are two linear layers, this is our formula. Yeah, you will be right that, we use two linear layer in a row. It's ridiculous, but it is a two example, theory, where we want to explain some things, so it's okay. Of course, you wouldn't use this neural network in reality, but we'll only want to explain some theoretical results. So we use such loss, MC loss. Okay, let's calculate the gradient of it, obtaining like this. If matrices are hard for you, you can use, one-dimensional cases, yeah, whereas V is is a number or might be a vector of two-dimensional, yeah, but you will get something like this. What is important from this, that this gradient or the ends in X, where X is line ahead. Yeah. Then another assumption is that what is in terms of vectors in domain and out of domain. Out of domain, if we have domain, it's like a surface in space. And out of domain is some surface that is independent to our in domain. So in fact, we can say that in domain and out of domain vectors are perpendicular. Yeah. So right angle between all these vectors. So next we will use can say in domain and out of domain axis, and they are independent or right angle between these vectors. Okay, so we take x. Oh, sorry. Give me just a second. Yeah, I set incorrect notations. X is input, of course. B is backbone. V is linear layer. Okay, like always, X is always input. Sorry. So we can, if U is our out of domain vectors, then if we multiply gradient by U, we will get 0 because it ends with input, and multiplying x on U is 0 because we have right angle. So from simple geometry, we know that cosinus from U and x is 0 because it is right angle. So if we multiply x on U, we will get its scalar product, and it's because of cosinus, it's 0. It's okay if you don't understand all things, but I want you to understand the idea only. So if you use any optimizer like SGD, for example, yeah, you can see during fine-tuning, we update backbone, yeah? So we take gradient on backbone. What is BK? It's not a degree, it's the iteration. Yeah, because we have many iteration during SGD, for example, and it's kth iteration, kth weights on step K. So we take weights on step K, take scalar, multiply it by gradient, and take difference between weights and update. And multiply by U. If we multiply by U, we will see that, yeah, in fact, SGD seems like this without U. This is the formula. B on step K plus 1 is like this, yeah? And if we multiply by U, we can see that if we multiply BK plus 1 by U, we'll see that it's the same as here, but this one, yeah, is 0 because gradient on U is 0. So it's the same as multiplying B on step K by U. So the multiplication by U doesn't change. What does it mean? This means, what is multiplication by U? It's scalar product. In fact, it's like projection. So projecting on OD space, out of domain space. During fine-tune, the projection on out of domain space doesn't change. That's the key idea. If you didn't understand the formulas, it's okay, but that you should catch the idea. Give me a second. Yeah. Yeah, like this. So during fine-tuning, we take us, we take yeah. This is for example. Let's take say the right thing. During fine-tuning, W star are the ground truth weights, yeah, that we want. And during fine-tuning distorts pre-trained features. What does it mean? Yeah, this is the conclusion of previous formulas. This means that if we make fine-tune, the pre-trained features change dramatically, and many of the information from previous stage, from pre-training, distorts. Well, because as you can see, we go like this because the projection on OOD should be the same. Yeah, and we want to minimize the error with W star. But saving the projection. So if we have, for example, backbone like this, after it we use linear layer. If you remember, yeah. In our case, it's one-dimensional, so we only multiply the vector. So after fine-tuning, after feature distortion, well, we changed backbone. What is the optimal step to get as close to double star as we can? Talking about in domain. We can multiply the vector, so let's multiply in such way that the projection of W star and our W will be the same to minimize the error on in domain. So we see that backbone changed dramatically and feature distorted. Talking about lin-prob, we don't change our backbone, it's the same. And after we only train the linear head, so we only can multiply. Yeah, because linear in case of one-dimensional is multiplying on some constant. If it's a example, I will know this. So we will get something like this, and out of domain is as small as we can. Okay, a little bit hard, but next it will be easier, I promise. I don't want you to focus on this. I want you to focus on the idea. I will clear all drawings. Okay, so what is the idea? During fine-tuning, we internalize network head with random weights, and because of it, on first steps, when the weights are bad, the gradients for network head goes increase the quality of head. But because of bad gradients, because they started in the random linear, they also change a lot body. What I mean? For example, let's say that we freeze the head and train only backbone. Because the head initialized randomly, so very bad, the backbone will try to help the head to work good. So it will change dramatically, yeah, and in a bad way. Because if we would take good head from first, yeah, it will take good features and return good result. But because we take random initialized head, the weights of backbone change a lot. And very often in a bad way on first steps. After first steps, at the end, the head is rather good. So backbone starts to weights of backbones starts to work as they wanted to extract the good features. Yeah, but on first steps, for example, we want to minimize the function, like something like this. And if during pre-training we were in ways of backbone that were good, but initialized randomly, first steps we do random steps because we have bad initialization. Goes like this. This is where we want. Sorry, not so. Like this, I don't know. This maybe, this. And okay, after first steps, we have a good head. And after we started to minimize the function good in a good way. But for example, we can go to another minima or something like this. So first steps first gradients are about be random. They're bad. And they make the backbone worse. Okay. This is the problem that goes from these formulas, these graphics. So you can understand this problem like this in more intuitive way. On first steps, we make bad steps because of a randomly initialized head. What we can do with this? In one hand, we have fine tuning with the problem of randomly initialized head. It works well on in domain test, as you see, but bad on out of domain. Because on in domain, again, intuitively, you need very, very small number of steps to make line ahead works good. But on out of domain, your features are not so well do not work so well on out of domain because it's another domain. For example, sketches or pictures, and features are not so good. So you need more steps, and your result is worse. But linear probing, it works better on out of domain because you don't change backbone. But now it works worse on in domain because you don't change backbone. Yeah. Because you need to change backbone. So the idea is that you need to change backbone a little. If you don't change backbone at all, you don't have enough accuracy on in domain. If you change backbone too much, you don't have enough accuracy on out of domain because this is too much. Goes worse on out of domain. The idea is simple. Let's first use linear probing, and after that, use fine tuning. So, in first steps, you use linear probing. You don't change backbone. So the backbone stays the same, and you obtain a rather good linear head in the end, like after linear probing, for example, 82%. And after you use fine tuning, and because the line ahead at the beginning is rather good after linear probing, you won't make bad gradient steps. So your gradients will be good, so your steps also will be good, and you won't make and you will not make backbone very bad. It's in opposite. You will make it better. And the tests show that this method, LPFT linear probing, fine tuning, first linear probing, then fine tuning, achieves results, but even better than every of the previous methods, both on in the main test and out of the main test. In fact, the results on in the main tests are rather comparable to fine tuning. But on out of domain, it's dramatically better than linear probing. Okay, that is fine-tuning, linear probing, the differences between them, when you should use fine-tuning, when linear probing, and the method line probing fine-tuning that combines both methods and achieves better results than both of them. Any questions? I know a little It was a little hard maybe in stage of formulas, but as I said, you can catch the idea that fine-tune that if your line ahead is badly initialized in the beginning, you will you make your backbone weights worse at the beginning, and this is a problem. Okay, so conclusions you can see like this. What is interesting, as I said, in-dimensional features are distorted more than out-of-dimensional features. So during for example, as you can see during fine-tuning, the distortions are bigger than during lin-prob and fine-tuning. So fine-tuning makes your backbone worse. Now, this shows that fine-tuning makes your backbone different than after pre-training. But in fact, that means that it is worse. So linear probe fine-tuning doesn't change your backbone outputs so dramatically. And it works better. Okay. Another part of our lecture is CLIP model, Contrastive Language Image Processing. What is the main idea of this model? That it combines two modalities, texts and images. Let's talk a little about how it was trained and what about architecture. The main idea is that there are two encoders, text and image encoder. Text takes texts and image encoder takes images. There encodes images and texts. For example, we have n texts and n images. Yeah. After that, we multiply each image encoding to text encoding and get a matrix. Yeah. Of similarities. First, we have a batch of n samples. Each sample is image and its caption. For example, we see here an image of a puppy and a text. I don't think it is English, but it's like about it is a puppy. I don't know. Let's say it like this. Yeah, and then we encode each text caption and each image, and take n encodings of images and n encodings of text. And we know that first image and first caption are relative. So first caption is about the first image. Second caption is about second image. And when we multiply each image to each text, I get matrix n on n with numbers. Yeah, with numbers. We want what we want. We want the matrix to show that first image is relative to first caption, and so on. So on the main diagonal, the numbers are small, and in other cells, the numbers are big. So small numbers show that distance between encodings are small, and big numbers show the distance between encodings is big. In fact, what our encoders do, they project each text or each image into the same space, yeah, and with a metric on it. Metric is multiplying, yeah, something like this. In fact, what multiplying means? It means cosine similarity, as we can say, because if we have two vectors, yeah, for example, I and t or something like this, yeah. What we do when we calculate scalar product? If the length of each vector is 1, if they're normalized, in fact, scalar product is equals to cosinus between these vectors. Yeah, so cosine similarity, and the smaller the cosinus, the bigger the value, because cosinus of 0, the smaller the angle, the bigger the cosinus, because cosinus of 0 is 1, and the bigger the angle, the smaller is cosinus, something like this. Because, for example, cosinus of p is -1. So it's like space and magic. So there are coordinates in the same space, and we want to bring together embeddings of pairs. So image caption, for example, puppy and image of puppy and text. It is a puppy. We want to bring together in this space and push apart embeddings from different pairs. For example, image of fox at the end and text. This is a puppy. We want to push them apart. This is the idea of clip. So the data is pairs of image and its caption, and architecture is like this. What we can do with it? For example, if we have image and we want to classify it, for example, plane, car, dog, bird, something like this, we can put the image into encoder, get the encoding of this image, then take all classes we want, encode this a photo of a car, of a dog, encode these classes into these, and then count the similarities and consider them as logits. So the probability of the class, something like this. And take the similarity score and take the best similarity, the smallest. And the result will be, for example, in this case, a dog. And this names as zero-shot approach. When we, for example, when we get a new data set, we take with classes inside clip, and clip has a really large number of classes. Then we take encoder, image encoder, encode the image, and obtain probabilities of classes and take class. So without any training, we obtain a method how to classify your images from your dataset. That's cool, because as I said, number of classes in clip is rather big. So you can use this zero-shot approach. So zero-shot because you need 0 examples to train. So you don't have training. Okay. And let's talk a little about loss. The idea is to take each row and use something like cross entropy, because you have, in fact, for example, for row 3, you have a right class, right probability, and other should be small. And it's the same approach as cross entropy. You take this is a true class, and these are false classes. And you do the same with columns, and sum 2 cross entropy losses for rows and for columns. Not really hard. As formula, you can see like this. Exponents, you divide it by t. It's a logit scale. So you multiply views of images, encodings of images and texts. This is similarity loss. Divide by t. It's a logit scale. Take exponents like softmax and use cross entropy. This is for rows, for example. This is for columns. Any questions? Don't forget to ask. Anybody alive? Okay, great. It's clear. As I said, CLIP is a strong zero-shot predictor. CLIP was tried on different datasets, and you can see that on top green bar, it outperformed different models. It was compared to ResNet 50 lin-prob. You take ResNet 50 pre-trained and lin-prob it on each dataset. And a clip showed zero shot without linear probe clip showed better results than linear probe on ResNet for these datasets. And for blue datasets, it showed worse results. So, but you can see that it's rather good. Clip didn't see any pictures from the dataset and classified correctly many of the datasets, better than ResNet 50 after linear probe. And on the right, you can see that zero shot clip outperforms few short linear probes. What is interesting, that linear probe clip also outperforms others because it has a very good pre-training. Moreover, zero shot clip is a very robust model. It works good on out of domains data. Yeah, as I said, you can see photos of bananas. Then you can see other domains. I don't know what is this, but for example, these are sketches of bananas. These are bananas in house. I don't know. Yeah. And you can see that scores are good compared to ImageNet ResNet 101. Yeah. So we see that good pre-training is very, very important. How to connect clip model to our fine-tuning and linear probe techniques? As I said, zero-shot clip is rather good. I will remind you what is zero-shot clip. For each class we encode each class text and get encodings of classes. In fact, before inference, so we have these classes encodings before, and after we take each image, get encodings of it, count similarities to classes because now encodings are in the same space, and get the result. It's zero shot. In fact, we can consider these encodings as linear layer matrix, because in fact, how we can obtain this row E1 multiplied on every T. We can take matrix of T rows and multiply it on E, and we'll get the same result. So in fact, zero-shot clip is using image encoder and linear head. Okay, but let's take this linear head as initialization. So we will initialize linear layer matrix with these encodings, and we'll get a good model that works rather good. And then we'll fine-tune our linear probing on our small data set with labels. And we will avoid, for example, problem that our linear head is initialized randomly at the beginning. Yeah, as we discussed, that it is a problem. And for example, line probing LPFT technique can help us to avoid it. But now we have a good installation, and we, for example, can use fine-tuning from the beginning. I don't know. Yeah. And we will get a good result. So if we have a task, classification task, a good approach is to take clip model, take text encodings of classes, and fine-tune a model on this dataset. Because in many cases, your dataset is not very big, and clip was pre-trained on very, very large dataset with pre-trained images, and it will boost your result dramatically. There are some interesting details how to use clip correctly. For example, we can encode a photo of a car, but there also can be a text, an image of a car, you can see a car on the image, and so on. So many captions. So if you will take many captions, many templates, yeah, like a photo of a object, and then take the mean of all these embeddings, that will work better. After, don't forget to normalize the embeddings of image and the text, and use the distance. Yeah, something like this. I will send you an example notebook where you can check it. Or I think we'll have time to check the notebook now. Give me a second. Sorry, forgot to mute on. Let's see how zero predictions can be made. We took a notebook from my classes. We can use clip library. It has image encoder with pre-trained weights. So the idea is we want to take zero shared weights. We iterate over class names like banana, apple, orange, lemon, I don't know. In each task, you have your own class names. And then you iterate through template. What is template? Again, you can use a library with templates. Okay, give me a second. Yeah, you can check this GitHub and find the templates, I think. Yeah, so insert src templates. What is template? As I said, it's like a photo of an object. I will show you the example. Give me a second again. Yeah. Like this. This is GitHub. You see a templates folder. For example, let's take OpenAI ImageNet template. So embed photo of a photo of many, a sculpture of a, and again, instead of C, you put apple, orange, and so on. So very big, large amount of templates. You can see the toy orange, for example. So it's not something rocket science. Okay, so we iterate over each template and append to text. Yeah, we append to text a new phrase. For example, we have a class name, yeah, as I said, and for example, we can put a photo of an orange. Yeah, where class name is orange, a photo of a. Okay, after we tokenize the text with clip library, get the embeddings, use text encoder, normalize the embeddings, mean them, and again normalize. Something like this. To tell the truth, I'm not sure that we need to normalize before taking average, but let's make the same as our authors. So we have embeddings, add embeddings to weights, yeah, for each class name. So this is our row, and after zero short weights are isometrics that we want to use as linear layer. Of course, we also use logit scale. It's divided by t, as I said. And that's all. We have a classification head with our metrics. So it's not very hard to do. Then we use our, again, image classifier from clip from this GitHub. In fact, it takes a clip image encoder and our classification head that we passed. We use image of banana, processes it into tensor, and make prediction. We get logits from classifier and make softmax because we want to see probabilities, not only the result. And after we can see that we have probabilities for each class. The probability of banana is 99%. So it is banana. So this is how we can work with it. I will send parts of this code also after the lecture, but you can use zero-shot model to classify something. And of course, after you can fine-tune it or linear probe if out of domain. Yeah, if you want to improve results. If you have a data set that you want to train on, you can also use it. And the big advantage that Clip has seen a very large amount of data during pre-training, and you didn't do this pre-training yet, you can reuse the results, and that makes this approach very good. Okay, any questions on code maybe? I think we will end at this point. So if you have any questions about the whole lecture, any feedback, I don't know, you can mention it. You can ask questions. Okay, great. Thank you for your attention. Bye. Have a good day.